Okay, so we'll be starting off with the last tutorial for this course, and in this tutorial we'll mainly discuss about the solutions of assignment number 7 that were given to us. And after solving that, if there is still time, then I plan to solve one more question that is similar, like a problem solving approach, to get to like let you understand the problem solving approach of this type of questions. So we'll see that whether we get time to do that or not. So for now, I'll just start by solving the questions for assignment number 7. So first of all, let me just take the questions and then answer them one by one. So this is our first question. Okay. Just give me a minute so that I just copy paste the questions and then we'll start solving. Okay, so we have 4 questions. This is question number 2, and each of them has the solutions answers given, and I think most of you have already solved and tried by yourself to solve these questions, and if yes, then you can match your solutions with me and let me know if there is any problem in any questions. Otherwise, if you have not done, or if you have skipped any question, then you can just look at this solution that I am doing and you can get the idea from there. Okay, fine. So we are done copy pasting 4 questions. Now let me go to full screen so that it is more clearly visible to you. Okay, hope the screen is visible. So now we can start. Okay. So let us see our first question first. That let us read the question. I hope this is visible properly. Okay, so it is asked in that question that we have been given a table where the table shows entropy versus energy of a system. Okay, um, just one second. Okay. Yeah, so I was saying that we have been given a table, and the table shows entropy versus internal energy, or U. U is the energy and S is the entropy of a system of identical charges that are stuck to a labeled corners of a tetrahedron. So first of all, we need to understand what is the system that is given in the question, what is the type of the system, how you can construct the system. The idea is that you have a system of all the charges as identical charges that are stuck to the leveled corners of a tetrahedron. So as if you have a tetrahedron shape, and in you know that a tetrahedron has 4 corners, right? So you level that 4 corners by 1 2 3 4 in a specific pattern, and in each of the corner there is a charge that is sitting on the corners. Let's say the charge that is sitting in each corner is identical to each other. As in that, if you assume that electrons are sitting in those charged corners, then you can take that each charge occupies a E charge in each of the corners. Okay, there are 4 corners, so 4 E charges, and they are stuck to the corners. And if it is a tetrahedron, then you know what is the shape of a tetrahedron basically. So if we just roughly draw a tetrahedron here, then you know that this is somewhat what the shape will look like. So this is a tetrahedron, and these 4 are the 4 corners of the tetrahedron. Okay, so you can name them by 1 2 3 4 in any pattern you want, but you should be consistent with the numbering. So I am taking 1 2 3 and 4 in a clockwise manner I have taken. And the catch is that in each corner you have a charge sitting and they are identical to each other, so all of them are, let's say, E charge, electronic charge. And because a tetrahedron has equal side lengths, so you take that the side length is a for each of the sides. Okay, so if this side is a, then between this 2 and 3, this side is also a, then this is also a, here this is also a, and this distance is also a. So a is the length of each of the side of the tetrahedron, right? And for such a system, so this is now how you can define the system. And now for such a system you have to calculate the entropy, which is S, and the internal energy of the whole system, which is U. And you can see from the chart that four values are given, right? So it is as if you have to go one by one, like first of all, for single charge you calculate what is internal energy and entropy. Then for two charges, what is the U and what is the S value. Then for three charges, what is the U and S value. And finally, what is the U and S value for all four charges. So this is basically what you are asked in the form of a chart in the question number 1. Now you have to answer that by calculation, that which one of the charts is the right answer. Okay, so let us start solving then. So as I said that first let us define our system. The system given or asked in the question in question number 1 is a tetrahedron. So let us draw a clear tetrahedron structure first. Okay, okay. So I hope you can get the idea of a tetrahedron, even if I am not drawing very accurately, because I am drawing by hand, so it might not be very accurate, but I hope you get the idea. So these are the four corners of the tetrahedron that I am marking in red intentionally so that it is distinctively visible. Okay, and each of the corners has identical charge as asked in the question, and we take the charge as E. Okay, so all the corners have a E charge present, right? Now there is one other thing is that each of the side of the tetrahedron are equal in length. So that is what mostly happens for tetrahedrons, that you have a equal side length for each of the sides. Okay, so we take the side length is equal to A. Now, this part is A. Then again, in my drawing the lines may be a little bit distorted because I may not be very accurately drawing it, but just get the idea. Okay, so this is A, this is also A, this is also A, and similarly from here to this corner, this is also A. Okay, so also one thing is left is that we have to number we have to label each of the corners, because in the question it is asked that you have been given labeled corners of the tetrahedron. So if we start labeling, let's say we start labeling in a clockwise manner. So if this is 1, so this vertex over here we label as number 2, then this one as number 3, and the last one as number 4. So these are the 4 labels to the 4 corners. Now, so what we have is a tetrahedron. Now 4 corners or 4 vertices of the tetrahedron are labeled clockwise. Now this is by our choice, you can also take an anti-clockwise manner. What matters is that you number them and label them properly, and we label them as 1, 2, 3 and 4, and each labeled corner has identical E value of the charge stuck to it. Okay, and also the other thing is that each side length of the tetrahedron equal to A. So that is what we saw, that even if you take 1 to 2 or 2 to 3, 3 to 4, even 1 to 4, 1 to 3, all of these sides that are possible, each of them has a equal length, and that is A. Alright, so this part is up to this is fine. Now what happens is that you have been asked to calculate the energy of the system and then entropy for the system. Okay, now you know that for this kind of a configuration, the first thing that comes to your mind is that any kind of interaction that is possible in this case will be interaction between charged particles. So you know what is the most common idea about that is the Coulomb's interaction that is happening, that mostly happens for charged particles, and that Coulomb interaction force has a specific universal structure. So if it is an interaction between charged particles, because each of them has a charge of E in each of the level corners of the tetrahedron, so this will be a Coulomb interaction, right? Coulomb interaction. And you know the general idea of Coulomb interactive force, F is equal to some constant K, Q1, Q2 by R square. And in this case, the energy becomes just K, Q1, Q2 by R, where there is necessarily a negative sign in this case if F is positive, but let us not right now focus on the sign, because you have to, in the question it is mainly asked about the magnitude. So, and the sign can vary depending on whether it is a repulsive kind of an interaction or attractive, so we'll not bother about that much. Okay, so let us not bother about the sign here, just take the values as it is. Okay, so now here this is your Coulomb force, that is a very common form of the force between charged particles. Coulomb force between two charges which are of charge Q1 and Q2 separated by distance of R. Okay, and similarly this U here is nothing but the interaction potential. So this is basically your Coulomb's interaction energy or potential, whatever you can say. And here also instead of R square there is R, because this is energy. So this R is the distance between the two charges Q1 and Q2. So the idea is that if you have one charge here and one charge here, this is Q1 and this is Q2, and if the distance between these two is R, so then what will be the structure of the force is this thing, and what will be the structure of the interaction energy between them is this thing, where K is a constant, universal constant. For this case we can ignore K, or we can take, for simplicity we can assume that K is 1, just like we do in most of the cases. For the ease of calculation we take all the universal constant values to be equal to 1. Assume K equal to 1. Then what happens that U equal to just Q1 Q2 by R, because we have taken K as 1. Now this U you have to calculate. This is one thing for the system of tetrahedron with each of the level corners with a similar charge of E. Now this you have to calculate, and the corresponding entropy also you have to calculate. So let us first try with what is the point for U, and then we'll go for the calculation of entropy. So first of all the calculation of energy U. Now you might have noticed that in the question there are 4 values are given, right? So U has 4 values: 0 is square by A, 3 is square by A, and 6 is square by A. So this is happening because they are taking one particle at a time, as if you are first of all, when you start initially you have 0 particles sitting. Now you place one particle of the tetrahedron corner and to begin with, and then you keep on introducing new particles up to 4 particles, which covers your all 4 corners of the tetrahedron. and at the time of introducing each new particle you have to calculate what is the total internal energy or interaction energy for the system. That is why you have been given in the chart 4 values of u. So first of all, what is the first value of u is that when we first introduce a charge E to our system, that is for the first charge initially, there is, because there are no other particles to begin with, right? When you are placing and taking this, let's say we start with level corner of 1, so initially there are no other particles present, and then you just take an E charge and place it here at the corner of 1 and mark that corner as level 1. So because there are no other charges present initially, so there is nothing to be to interact with for this electron or this charge E. So for the first charge initially there are nothing or no charge, there are nothing to interact with for this E charge that is introduced. Okay, so if there is no charge to interact with further, so generally your U will be 0. Why? Because I just told you that when you are just introducing a first electron or first charged particle to your system, so there are nothing else so that this electron can interact with and build up an energy. So to begin with you have a 0 energy for the whole system, because you have 0 interaction scope for the particle. Ideally, because this is not of course an ideal case, because when you are placing a particle it has always a surrounding which it interacts with, but in this case it is as if taken as an isolated system where you have only particle when you introduce them and nothing more or nothing else to interact with. Okay, so for the first particle basically because there is nothing else to interact with for it further, so we take that the initial interaction energy for the system will be 0, and I hope this has no problem or conflict till this point. Now when you introduce your second particle, then the physics starts to change, because after you have introduced a first particle and you keep on introducing new particles, then you always have some other particle to be present there, so that you can have an interaction energy with the initial particle, right? So that is what happens um, when we introduce so this is equal to 0 when there's only E sitting at level corner number 1. Now when you introduce the second charge of the system, that is a second E charge to the system, then it has already a previous charge of E to interact with. Okay, it is already a previous charge of E to interact with. So what happens is that your now the interaction energy of the system, so net interaction energy of the system is equal to U, which is nothing but the interaction energy between particles 1 and 2, or charged particle 1 and 2. So basically if you assume that you introduce your second charge and place it at the second at the leveled corner leveled as 2, then already you had a particle sitting at 1, right? So already you had introduced this particle And now, as if you are introducing this second particle or second charge E and placing it here, so what will happen is that already being this particle present, this charged particle, so this will try to interact with the newly introduced particle, and so they will have an interaction energy between them, and this energy will be depending on the distance between these two charges, which is A, of course, because it is a tetrahedron of side length A, and the charges of the particles, right? So in this case it is easy, you just follow this general rule that E equal to q1 q2 by r from Coulomb's interaction between charged particle, and in this case your q1 is equal to q2 equal to E, because all the charges are identical, right? So in this case, and your r is the distance between the two charges, which is distance between the two charged particles of E, which is nothing but the each of the side length of the tetrahedron, which is in this case A. So your q1 q2 by r becomes E squared by A. So this is your second answer for the energy when there's two particles or two charged electron at both site number 1 and site number 2. So this first one is for only a single charge. Now the second, you want to this energy, this internal energy is the system of two charges E at a distance from each other. Now this is the second scenario also done. Now if you introduce your third particle, third charge E, if we introduce our third charge E, then what happens is that now it has two more charges from earlier, which are charge number 1 and 2 at the level sides of 1 and 2, charges from before to interact with, right? So if you look at the picture, as if you have already placed this charge and this charge, these are already there. Now you introduce your particle number or charge number 3, which you place at this corner labeled as 3, and then what does this electron see? This electron sees that it has two more electrons placed from before to interact with. So this electron can have an interaction with this electron with site number 1, and with also an interaction with this electron site number 2. And not just that, don't just get mistaken by that there is only two possibilities, but there is also a possibility that your electron number 1 and 2 are still there, right? So they will also have an interaction in between them. So because you are talking about the overall system, so you have to take into account the individual interaction energies between each of the pairs. So you cannot neglect this interaction energy that is already happening between particle number 1 and 2 just because they were from before. So you have to take that also into account and add that up with the newly introduced energy because of the new particle at site number 3, and you basically sum up all the three contributions. So which are the contributions of energy in this case is that one is this already present energy between 1 and 2, which is like U1 2, you can identify it like that. And then because you have now introduced particle number 3, so it can have two possible interactions. One is with 1, which is U13 here at this line, and the other is between 2 and 3, which is like U2, 3, between particle number 2 and 3. So you have now for the whole system, if you calculate, you have now three energy terms and they add up to give you the net energy for the system. So your net energy for the system U is equal to basically U1, 2, which was present between the two particles from earlier. Then because you have introduced a new particle 3, so it has an interaction with site number 2 with charge E, and also an interaction with the charge E at site number 1. So now remember that this was already present from before between 1 and 2. And these two terms, these are newly introduced terms due to the newly placed E charge at 3 interacting with 2 previous charges at 1 and 2. Okay, so if that is the case, then you know that your U12 was what? This is E squared by A. This was already calculated. So obviously this is E squared by A. Now if you consider U23, so what you see is that U23 is basically along this line between 2 and 3, where two charges E and E are separated by the same distance A. So this is also E squared by A, right? And similarly, if you are for U13, again you have two charges at 1 and 3, both are of charge E, and they are separated by a simple same distance of A, because it is a tetrahedron, so it has this property. So again this interaction between 1 and 3 is also E squared by A. So what you get is that a summation of 3 E squared by A's, so this is also E squared by A and another E squared by A, so you get 3 E squared by A. So this is the net energy when you introduce a third particle to the system. 3 particles. Okay, and for the final case, when you finally introduce your last or fourth particle, so when introducing the last or fourth particle of the tetrahedron, right? So introducing the last particle of the tetrahedron, because initially we have already completed the 3 sides to be occupied now. So now the fourth particle is introduced. So let us look at the picture again of the tetrahedron. So this is our fourth particle. Let's say we place it here. So what does it see is that it has already 3 particles around it to interact with. So this particle will see this particle at 1, this particle at 3, and also this particle at 2. So these are the newly found interaction terms that will be present there because you have introduced the particle at 4. But also you don't have to you must not forget about the previously present interaction energy terms of the system, because you cannot neglect that. Just like you have still the interaction between 1 and 2, and also the interaction between 2 and 3 and 1 and 3. So basically you had already these 3 terms present, U12, U23 and U13, and now you just introduce 3 more terms to the system. By what? By this newly found interaction terms between this new particle 4 and the previous particle 1, so it is U14 along this line, and similarly between the new particle 4 and old particle 3, so this is U34 between these lines, and also with particle number 2 with the new particle 4, this is U24 along this line. So what you get is that now the total energy net interaction of the system, so net U is equal to the previous terms, which is between 1 and 2, the previous energy is between 2 and 3 and between 1 and 3, and finally these are all the old terms that were already present at the previous step, which is giving you 3 squared by A. These are the old terms, and there are some new terms that are introduced because of the new particle in the structure, which is like U14 plus U24 plus U34. These are newly introduced due to charge that is placed at 4. But because also in the last case you have the similar 2 charges E and E separated by the same A distance here, here and here also. So again each of the terms will be having a value of E squared by A. So these three terms are 3 e square by a, and the last three terms are also similar, each e square by a. So basically you have 6 terms, each having e square by a. So this is 6 times e square by a as a value of energy. So this is for the case when all 4 charges are at 4 corners of the tetrahedron. Okay, so basically we have now solved the calculation of U. Now you have to get the value of the entropy also for the same configurations. So what you do is that calculate entropy is for all these 4 steps. The steps for which you have already calculated your U. Now we have to calculate your entropy or S. Okay. So this will be easy. Basically, first of all, remember that when you have no particle from before and you just introduce your first particle to the system, then first of all what is entropy? Entropy, if you remember, entropy is nothing but your this formula that A is equal to kb ln omega, where kb is the Boltzmann constant, which is often taken as 1. So A is equal to nothing but ln omega, where omega is the number of possible microstates in the system, or it in other words can also mean in how many ways you can arrange the system so that the macroscopic properties of the system remains the same, but microscopically they are different. Or if you have a number of particles, then in that system of particles, omega will be how many number of ways you can rearrange the particles, okay, to have a different energy at each time. So similar to that, we if you once calculate omega, then corresponding to that you can just take a ln or log, and you will get a entropy or S. So that is what we will do, is that first of all the first step is that when we introduce our first charge E to the system, then what happens is that first of all here it is important is that in how many number of ways you can introduce or place your first electronic charge E in the tetrahedron structure. So this can be misleading in some terms, that when you introduce your first charge, then basically you have nothing to begin with. So this is what you begin with, you have nothing from before that is present there. So it does not actually matter that where you place your first charge, because wherever you place your first charge, that's what actually begins to form the structure. So before this, even if you imagine a tetrahedron, you cannot just label the tetrahedron corners as 1, 2, 3, 4 until and unless you just start introducing a charge to it. Other than that, all the corners are equivalent, right? Because all the corners of the tetrahedron will look just the same. So there is no individuality between any of them. So only when you start to introduce a charged particle or charge to one corner, then that corner becomes significant compared to others, and you just start to number them all or level them all. So basically initially when you introduce your first electron, then as if the number of ways to do this, to place this electron in the tetrahedron equal to omega, which is the number of microstates, same as the number of microstates, it is nothing but 1. Why 1? Because even if you have 4 corners to place the charge, okay, even if you have 4 corners to place the charge, but the number of ways to do this is only 1, because it does not matter whether you place the charge here, here or here or here. This will only matter once a structure is being formed, but initially when you just take one single charge, you can just place it anywhere, this thing or here or here or here, it does not matter, because there is only one way to place it. Once you start putting the other charges, then the tetragonal structure actually forms, and then each of the corners becomes significant on its own. So initially when you just have one single charge and no structure has been formed yet, so you can say that your number of ways to do this is 1. So in that case, your entropy is equal to ln omega, which is ln 1, that is nothing but 0. So for the first step, your entropy is 0. Now for the second step is that we introduce second charge E to the system when there is already a first charge E that is sitting in one point. Okay, so now after this point the physics becomes different. Now you have already a structure starting to form where you have already a charge that is present. You have to take that into account, and now in how many number of ways you can have two charges by introducing the second charge to the system. So number of ways to arrange two charges among all four corners of the tetrahedron equal to nothing but your 4C2, as if you have four places to select from and you have two charges to put in them. So you take the combinational approach 4C2, and which is nothing but your 4 factorial into 2 factorial into 4 minus 2 is 2 factorial. So this is your 4 into 3 into 2 factorial. This is your 2 factorial into 2 factorial. So this cancels out. 2 factorial is just 2. So this is 2 into 2, 4. And this is 6. Okay, so you have got 6, and as a omega value, this is the number of ways, that means it is omega. So your S equal to just your, sorry, so your S equal to just your K ln omega or ln 6. Okay, so second step is done. Now what is the third step? Is that you introduce your third charge E to the system when you already have two previous charges E sitting at two corners of the system. Now again the idea is same, that you have total 4 places to keep the charges, and you have 3 charges in your hand where you are introducing just the third charge. So how many number of ways are possible there? So number of ways to arrange or place three charges at 4 possible corners or possible places of the tetrahedron is nothing but your 4C3. So you have 4 possible places to select from, and you have 3 charges to put in them. So it is 4C3, which is again nothing but 4 factorial to 3 factorial into 4 minus 3, which is 1. 1 factorial is just 1. So this is just 4 into 3 into 2 factorial, or in other words, this is 4 factorial. You can just divide it, you can just break it down as 4 into 3 factorial basically. So this is 4 into 3 factorial divided by already a 3 factorial into 1 factorial is 1. So this cancels out, and this is just 4. So in this case your S equal to K ln omega. So this was your omega. So omega is 4. So S equal to just ln of 4 for this third step. And finally for the last step or fourth step, or last step, is that number of ways. Now you have all 4 particles, because you had already 3 particles sitting in 3 corners of the tetrahedron, and you just have to place your final particle, that is particle number 4. Now even in simplest idea, without just taking any combinational mathematical approach, you can just think of it like you already have selected the places of 3 particles beforehand, and now you have just one more place left, and that the place that is left will be occupied by the fourth particle. So while placing your fourth particle, you don't have a choice that, where specifically you want to put it, because you have only one choice, and that is the place that is left after the three particles got occupied, are occupying the other places. So the number of ways to place the last particle in the last and only single available place is omega equal to 1, or you can say this is like 4C4, as if you have four possible places and four particles you have now in your hand to place them into. So how many number of ways is just 4C4 combinational approach, and this is again 4 factorial by 4 factorial into 4 minus 4 factorial, which is 0 factorial, nothing but 1. So this is 4 and 4 factorial cancels out, and this is just 1 by 1 into 1, and this is just 1. So your S is just ln of 1, which is 0. Again for the fourth step you have 0. So now if you compare your all the four steps and what is the result of U and S corresponding to each of the step, you get that for first step S is 0, second step it is ln 6, third step it is ln 4, and the fourth step it is again 0. Similarly, for the internal energy or U values, for the first step your U value was 0. Then for the second step your U value was just E squared by A. For the third step your U value is 3 E squared by A. And for the last and the fourth step it is 6 E squared by A. So what is done is here that if you just have to take or form a chart, then you can just say it like this. This is U and S. So for the first step, you know that your U is nothing but 0, because there is no other particle to start interacting with while introducing your first particle, and your entropy was also coming as ln of 1, that is again 0. For the second case, you have only one particle to interact with the second particle, so only interaction between them is E squared by A. And in this case, your ln value came as log 6 or ln 6, whatever approach you use. To match the answer, I have taken the ln as log, so it is the same thing, you know. So this is the log 6 for the second step. Then for the third step, you have three particles, and each of them will have mutual interaction between each other, Coulomb interaction, and they give rise to a force of 3 square, interaction energy of 3 square by A, whereas this entropy we have calculated as log of 4, depending on the number of configuration omega that is possible. Now for the last one, you have all four particles with each of the pairs having a separate individual interaction between them. So we calculated that this is 6 squared by A, and the entropy in this last case is nothing but 0. Okay, so basically this is your chart that is being prepared, that has been prepared now. This is your answer. If you can match, if you want to match it, so you can take at each of the step what is your values, how are your values are changing. So this is at first step, this is second step, this is third, and this is fourth or final step. So the first step is when you introduce just your first charge particle E to the system. The second step is when you have two particles. So this is here, this is when you have only one particle in the system. This is second step is when you have two particles in the system to deal with. Third step is you have three particles in the system to deal with. The fourth step is that you have four particles in the system to deal with. And we have found the answer. So let us match our answer whether it has matched or not. So we find that our answer actually matches, because this answer, you see, we have just got that 0 is squared by A, 3 is squared by A, and 6 is squared by A. Okay, so basically we have to finish all the other questions in time. So let me move on a bit faster now. So now the second question will be lengthier. So Third and fourth question are not very lengthy. This will be done in few minutes, but the second question will be pretty lengthy. So we need to do that carefully also because it includes a large calculation. So let us start with question number 2. So it is said that in the question that find the average of the square of the angular momentum in a harmonic trap problem. So always in a question, always first focus about what is the system that they have asked you about, and in this case the system is a harmonic trap. Okay, so harmonic trap problem is that they have talked about, and this is also you can find that they have discussed the same problem in video tutorial number 2, but in that case there are different different questions asked, and in this assignment that question that is asked is not had not been asked in there, but the idea of the problem is given in tutorial number 2. You can check that out. And it is asked that in case of that harmonic trap problem, if you have an angular momentum to the system, let's say which is L, and you just have to take the square of the angular momentum, that is L square, and find out what is the average of L square. So this is your typical this is the precisely the question you have been asked and which you need to answer. And here omega, which is nothing but your rotational speed, I think rotational velocity, is having a direction along the z direction. And also it is said that do it for a single particle. So in case of harmonic trap, there can be multiple particles, subatomic particles, that are trapped to the like a in a harmonical what is the simple harmonic, like a simple harmonic oscillator case, to a spring like thing. But that will make the problem much more complicated if you have to consider all the particles. Then you have to consider take a partition function according to that. But to make life simpler, it is asked in the question that just calculate for a single particle. So for these kind of problems, if you have been asked an averaging, so the statistical approach to is that you have to first find out the partition function for this case, which is z, which is a partition function for a single particle, which is, let's say take as z1, or sometimes z we can also take. This is a partition function for a single particle. Okay, and you have to find out this first, and once you know z, then you know that in any quantity you have to take a statistical average. Let's say if you want to take a statistical average of the quantity x, then what you do is that you just take that quantity x, multiply it by to the power of minus some beta into some energy E, then you just sum over all possible energy E, then divided by because this is the quantity you want to take the average of, so this is the multiplied here. This is the Boltzmann factor, where E is the total energy of the system, and then in the denominator you have again e to the power of minus beta E only, summed over all the possible energies. So as you know that the initial thing, this is x e to the power of minus beta E, where the denominator is nothing but your partition function z. So it is as if you have to you have to know the whole energy, entire energy of the system, that is E. Okay, and that will help you to get the Boltzmann factor. In this case, what will be the exponential term, and also based on that you can also find out what is your partition function, because partition function is the same factor when taken for all the summation of E, right? So these are the things basically you need to find out when you are asked about the average for any quantity in a statistical mechanical problem. So let us just first understand the question and try to solve it in our pattern. So this is question number 2. So this is a harmonic trap problem. Harmonic trap problem. Okay, and this is asked for a single particle. This is asked to do for a single particle. So this is important that you have to only use a single particle. Okay, so just to roughly draw the diagram, you can also find out the diagram had been drawn in the tutorial number 2 video that is already uploaded in the lectures sections. So this is basically if you have three-dimensional axis like this, x, y and z. Okay, and you can have just a particle which is, let's say, bound to the center with a spring. Okay, So this is some kind of a spring which has a spring constant of k. It is tied to the center, and this is the particle, subatomic particle, tied to the spring. And whatever displacement you want to talk about the particle from the uh, you know um, the distance of the particle from the center, that distance we take as r vector. Okay, so in this case basically the whole idea of harmonic trap is that you can have multiple such subatomic particles bound to the center like this with different springs. Like you can have other particles also, okay. Many number of particles are possible, but we do not go into that, because in that case the Hamiltonian to take the whole system becomes very complicated. So instead we just focus on what because this is a harmonic trap, so the force that will be acting on the particle is nothing but this kind of a force, um, F equal to minus kr I vector, which is the harmonic force that is appearing. K is a spring constant, and r is a distance or displacement of the particle from the equilibrium position, which is the center in this case, center of the coordinates. Okay, now to calculate for such a particle what is the total energy or Hamiltonian for this case will be a summation of its potential energy and kinetic energy. So you can take it like pi square by 2 plus half k ri squared. So why you are taking like this is basically you assume that the particle that has been taken here has a mass of m, okay, and it has a momentum of pi. Now why I am taking here I? So that is because I can vary from 0 to n minus 1. This is taken as a summation because when you assume that there are multiple particles present in the harmonic trap, which is actually the case, so let's say there are total n number of particles present in the harmonic trap, and so because there are n particles, so the indexing of the number of particles starts from 0. So because there are n particles and the indexing start from 0, so it will obviously only cover up to n minus 1. Okay, and when you have to calculate the entire Hamiltonian from the system, so you have to sum over all the potential and kinetic energy contribution from each of the particles, right, each of the n particles. So that is what has been done by the sum over I, and this pi is the momentum of each particle, momentum of each particle indexed by I. M is the mass of each particle, K is spring constant, and half kri square, you know, this is the potential energy that is coming from the harmonic force, or because this is attached to a spring. So this is your kinetic energy, and the second part is your potential energy, and Ri is the displacement of the particle that is marked by the indexed I from mean position of the particle, which is in this case the center of the 3D coordinate, which is here the center. So this is the total idea, and because this is in 3D, so you know that Ri square will be nothing but a summation of xi square plus yi square plus zi square. Alright. Similarly, if you want to take pi square, that will also be px squared plus py squared plus pz squared, because this is in 3 dimension. Okay, and so basically because when you are only asked about one single particle, then you do not bother about the indexing I, you just take one particle. Okay, and you do not basically bother about the index because then you do not have to take the summation over all the n particles, just a single particle. And the angular velocity of the particle, because you see that this particle here is as if bound in such a manner that it can also have an angular degree of freedom, as in it can also rotate in the spring can displace like this, like from this direction to in any direction possible, like in this other direction that I can draw. All these directions are possible in 3D, and it's as if the particle is not only having a spring type of a motion which is giving rise to this force and this energy, but also it can have a rotational kind of a motion also, because this can rotate throughout the coordinate system like this, in any direction it is possible. So that rotation will involve an angular velocity for the particle. So this is the angular velocity, and it is specifically asked in the question that your angular velocity has a direction along z cap. So you can take that your omega vector is just is omega into z cap, but z cap is your unit vector. And so Now if you are asked about the partition function for the single particle, so let us first derive that. So partition function, now this is for a single particle Z1, for a single particle, that is why it is taken as Z1, that is as if one particle, and this is nothing but your so you know that you have to take the Boltzmann energy term, Boltzmann factor, which involves e to the power minus beta times the total energy, right? E total. And initially you have to sum over all the possible energy values, and because we are taking a continuous energy, because the system can have a continuous energy value throughout the phase space, so instead of a typical discrete summation, you have to take integral over all the energy values, and that is done by taking an integral over the phase space. Phase space means you have both momentum coordinates and position coordinates, so it is like you have uh, dqp and d cube r, because these are all in 3D, so you have px, py and pz, that's why you are taking the element as d cube p for phase for the momentum space, and for d cube r is just dx, dy, dz, because this is again in 3D and this is the positional coordinate element. Okay, and this whole thing will also be divided by h cube, because this is the phase space minimum element, so whenever you are writing it like this, you have to also divide it by the unit of the phase space, which is having a volume of h, having a total coverage of h cube. So this is basically because you are taking an integral in phase space. Okay, phase space continuous integral over all possible states, right? So this is, I think, familiar to you from all the statmic problems. I do not need to um, elaborate further. Now what is important is that you have to know what is this E total. E total for a single particle for such a configuration is the kinetic energy plus the harmonic motion's potential energy, so we call it harmonic potential energy, and there will be an additional factor which we should not miss out, is that the rotational energy factor, rotational energy. So under kinetic energy, you know, this is just p squared by twice m, right? This is just p squared by twice m. Momentum, p is the momentum, and harmonic potential energy is nothing but yours coming from the spring motion, which is just half k r squared, and then your rotational energy is nothing but your omega dot L vector. So you can check that this is actually can have a energy dimension, where your omega is your angular velocity and L is your angular momentum. So what is L? L is your angular momentum, that means it is r cross p, where r is the position coordinate, p is the linear momentum, and L is your angular momentum, and the dot product of both of the omega and L gives you the rotational energy contribution, right? So this is your total energy that will be replaced in the Boltzmann factor in this e to the power minus beta times factor here. So if you want to write it like that, then Z1 is equal to just again d cube p d cube r divided by h cube. This is coming because of the phase space integral over all possible states, and then e to the power minus beta E total becomes e to the power minus beta H minus beta omega dot L, where H is nothing but only the these two parts, kinetic energy plus harmonic potential energy. This we term as H, and this is the additional factor coming from the rotation, and both of them is actually giving your total energy E total. Okay, so don't get confused when I write H. H is nothing but your p squared by twice m plus half kr square, right? So also if you can just want to simplify, what is this omega dot L, right? So omega is omega times z cap, and L is your r cross p. So you have to take what is this dot product can look like. So first of all, r cross p means if you take the cross product, it is just x cap, y cap, z cap, then x, y, z, then px, py and pz. If you take this cross product, what you have is that x cap ypz minus zpy plus y cap zpx minus xpz plus z cap xpy minus ypx. So it can have components along both along all three x cap, y cap and z cap. But because we are taking a dot product with only z cap, then all the other components along x cap and y cap will give you a 0 in the dot product. Only if you multiply the component of z cap with the z cap, you will have a non-zero value. So what will be the component is that omega z cap into z cap component here is this one. So here this is a dot product of x py minus ypx z cap. So z cap into z cap dot product is 1. So this is just your omega xpy minus ypx. Okay. So up to this I think this is clear. So then what you have to do is that you need to calculate your partition function z1. So you just have to calculate that integral that I wrote here in this case. So you have to break it down further. Okay, so to calculate the integral, you can just replace the values of omega dot L, just that, and also the value of h you can also replace because I have written it down already. Okay, so what will be the entire structure is that, let me write it down. Z1 equal to 1 by h cube is a constant, so let us take it outside the integral. Then your dpx, so your dqp, because I told you that this is a 3D, so dqp basically can separately mean this is your dpx integral, dpy integral and dpz integral. So this is same as your having dqp. You can break it down like this. Again also you have a d cube r, right? So if you want to break it down also d cube r, it will just become dx integral dy integral dz. All the three coordinates have an integral contribution. Now this e to the power of minus beta h, right? So e to the power minus beta h is nothing but your beta h is p squared by twice m plus half k r square. But again if you want to break it down in 3 dimensions, so p square is nothing but your px squared plus py squared plus pz squared by twice m plus half k r square is nothing but half into k into x square. R square is nothing but x square plus y square plus z square. So this is your entire e to the power of minus beta h that I have expressed by breaking it down in all the individual forms. Now there is another term coming from the rotational energy, which is e to the power minus beta omega dot L, but we have just calculated omega dot L because omega is along z cap is this one. So we just replace it here, e to the power minus beta omega xpy minus ypx. This whole thing is under integral of this all the position and the momentum coordinates. Now you have to separate term by term so that you can obtain the integral result carefully. So that's what we'll do. First of all, h cube constant to the other side, then just leave the momentum integrals to one side first and let us deal with the other ones. So this is e to the power of minus beta, then this whole the momentum factors we just keep it to the left for solving it later. So this we do not touch now. And then your dx dy, then e to the power, first of all we also take the x square and y square part separate, and only we so this has also this other term from omega dot L, that it is xpy minus yp. So if you look at this carefully, I have separated out all the terms regarding x, y, px, py and pz as well, and we have not yet written down the dz part. So dz part has only contribution from this other term that we have not written down yet, that we write down now, which is e to the power beta into half kz squared. Okay, so if you look at carefully, you see that all the rest of the terms does not have any z dependence except for this part on integral over z. So we can just take first focus on calculating this integral. So this integral is obviously from minus infinity to plus infinity, because that is the range of z. And if you try to get the integral result, you will just see that this is just a simple Gaussian integral, right? So it has a standard form of a Gaussian integral formula. And you know that you don't need to solve the Gaussian integral entirely, because this is a very standard result. And whenever you have such e to the power minus some constant, let's say if the constant is, let's say the general idea is that if you have e to the power of minus a t square dt, and the integral is from minus infinity to plus infinity, where t is the variable and a is the constant, then this is called a Gaussian type of integral, which gives you by default this result of root over pi by a, where the constant a comes to the denominator, right? So this is a very standard result from Gaussian integral. And also other thing I will also like to write down, it will come useful later, that if you have with this kind of a term, that t e to the power of minus a t square dt, then this kind of integral from minus infinity to plus infinity limit will give you a 0, because you have this odd t factor with this e to the power minus a t square dt. But on the other hand, if you have the same integral limit with t squared and then e to the power minus a t square dt, then you do not have the value as 0, but it is just 1 by 2a root over of pi by a. So these are the some of the standard integral results that are known from Gaussian integral formula function, which I will not solve explicitly for you. You can check it out by solving this integral by yourself by substituting the function variables, or you can check it from any math physics textbook, that these are the actual standard values of the Gaussian integrals already known to us. Okay, so whatever this part, this this dz integral will have a similarity with only this kind of a Gaussian integral, where this constant value a is nothing but your beta k by 2, right? So you need to replace this result with a value as beta k by 2. So what you have is that you can write down the whole thing, that this is just 1 by h cube, then dpx, dpy, dpz. So sometimes I may miss out the integral sign, but you just have to understand that the integral is there, because you have this dp element still present, right? So all the terms are separated, px squared py squared plus pz squared by twice m. Dx dy parts are also separated with this dx and y dependences. And also this rotational energy term dependence, which has also x and px, y and py both. And the final dz integral that we just solved here, we I told you how to solve it. So this will just be root over pi by the constant. So it is just root over pi by the constant beta k by 2. That means it is just 2 pi by beta k. Okay, so this part is simple. So this part is done. Okay, so I put it in a separate bracket. So because this part of the integral is already solved from the dz integral. Okay, now once we are free from any term or any factor in z, now we can focus on the solution of the other variable dependent terms. Let us say for first we try to solve what are the dependencies on x, so that we can solve the integral of dx. So what are those terms? Let us choose carefully. Is that integral dx, then e to the power, first of all obviously this part, e to the power minus beta k by 2 x squared. But not only that, you have also this part. This part has, from the rotational term, also has this x, which was not the case for z, because z did not have any other dependence, but x has part in this term. So you write that down. So it is e to the power of minus beta omega x py, right? So now you try to solve it. Now this is not the generic form of a Gaussian integral. No, this is also an integral from minus infinity to plus infinity. But for the simplicity of calculation, we'll try to reduce it in a Gaussian-like form and then get the answer directly. So how to do that? First of all, write all the power of exponential in full bracket. So this is e to the power of minus beta k by 2. If you take a common, this is x squared then this is plus sign because both are minus, beta is taken as common, 2 is taken half as common, so it is 2 times into all the rest of the terms omega x py, and because k was taken, so this is 1 by k, right? Now how can we further reduce that? You will express the exponential power as a some whole squared format. How to do that is basically you take x squared plus 2 times x. Now write it down like it is some x squared plus 2x into some y. So what will be your y? So this is your omega py by k, as if this is this 2ab form, and the b part is basically your b square will become omega py by k whole squared, because you have to adjust for that because you did not really have this term, so you adjust for that by omega py by k whole squared, taking a minus sign. And what it makes out of it is that minus infinity to plus infinity dx e to the power of minus beta k by 2. We just take that this term, this is as if like a square plus 2ab plus b squared, so this is nothing but your x plus omega py by k whole squared. And then this part is a separate part, so we just take it out separately, and what it becomes is that it is e to the power beta k by 2, minus and minus makes it plus, and it is simply omega squared py squared by k squared, which is nothing but this k and this k cancels out, so this is e to the power plus beta omega squared py squared by 2k. So what it becomes is, and basically also look at this term, that this is no longer dependent on x, so you can just take it outside the integral as a constant. So that's what we will do, that e to the power beta omega squared py squared by 2k outside the integral, and inside the integral you have a total Gaussian type of a structure again, x plus omega py by k whole square. So you can see that this is reduced to a Gaussian structure because you can always take a change of variable, and you can consider that this whole thing x plus omega py by k is your t, so that your dx is nothing but your dt, and if x goes from minus to plus infinity, so will t also will have the same limit. So this is nothing but your minus to plus infinity dt e to the power minus beta k by 2 t square. So everything remains the same, so you can just directly know the answer from the Gaussian integral's standard value, that this is this constant times root over pi by, again the constant here is beta k by 2, so this is just 2 pi by beta k. Okay, so this is the solution to your dx integral part that we have just solved. So you are just solving term by term because this is a large integral, so you have to solve term by term. So this is your dx integral, right? And similarly, you know that the dy integral will just be as similar to dx because it has the similar dependencies. If you look at it, that what are the terms that are dependent on y? So first of all, this term e to the power minus beta k by 2 y square, and the second one is this y px term, right? So you just take them, both of them together. Now the terms are dy to the power of minus beta k y squared by 2, and then e to the power of, this was a minus and minus, this makes it plus, e to the power plus beta y px. So it is e to the power plus beta omega y px. Again you can reduce it to a Gaussian form, and to do that you just have to take again the same kind of a formula and take it in a whole square format. So this is your minus beta k by 2 y squared plus 2 omega 2 omega y px by k. So this is nothing but your again follow the same manner that I did for the x integral. So it will be, I will just directly write down the answer now because this is just the same. So e to the power beta omega squared, instead of py here will be px, okay, because this is dy integral, and the rest of the terms are just the same, 2 pi by beta k. You can look for yourself that this is the solution that will come. So this is from your dy integral. Now once dy, dz and dx all are done, now you have to focus on the dpx, dpy and dpz integrals, right? So if that is the case, then you have to gather all the terms separately, like px terms dependent separate py and similar to pz. So what will be our integral? Now our z1 was before 1 by h cube common, and then if you remember the whole term, just let me go back. So this was your whole formula, right? 1 by h cube, and then all these integrals. These parts are yet to be dealt with, and these integrals I have already calculated. Okay, these part total up to here to here is already done by us. And what are the results that we got by that? Is basically this part into this part into this part. So we have basically root over 2 pi by beta k 3 times multiplied. So 2 pi by beta k to the power of 3 by 2 and multiplied by this exponential factor and this exponential factor. Rest of the terms are yet to be dealt with, that we will see below. Okay. So that's how we write it down. It is dpx, dpy, dpz to the power of minus beta by 2m px squared plus py squared plus pz squared. Then this exponential factor maintains e to the power beta omega squared px squared by 2k. Then the other one was e to the power this factor e to the power beta omega squared py squared by 2k. And then this 2 pi by beta k to the power 3 by 2. So 3 times, and there is a root factor, so this is half 3 by 2. So now it is the time for each of the variables to separate and to integrate separately. So the constant part comes outside. This is 2 pi by beta k to the power 3 by 2 and 1 by h cube comes outside. And inside your dpx integral will have your minus beta px squared by twice m to the power of beta omega squared px squared by 2k dpx, where px going from minus to plus infinity. Similar type of a factor will be coming for dpy also, because here also you have minus beta py squared by twice m, then to the power of beta omega squared py squared by twice k dpy. Only your dpz is separate with only one term e to the power of minus beta pz squared by twice m dpz from minus to plus infinity. Now let us start from the easier part. So if you just look at this part, this is a simple Gaussian integral. You know the answer. Here your constant part is beta by twice m, which is your pi by beta by twice m, which is nothing but your 2m pi by beta. So this part is done, and you have got to solve this part and this part, which are similar in nature. Once you solve one thing, you will automatically know the answer to the other. So how to solve this is basically I will do the one part for the dpx part, let's say. So you want to structure the integral properly. So what you do is that you take px squared as common, to the power minus px squared as common. So that gives you beta by twice m minus beta omega squared by twice k to dpx. So this is again your simple Gaussian integral, only now that this is your total constant term of a. So what will be the answer? It is just pi divided by beta by twice m minus beta omega squared by twice k. Okay. Similar thing, if you look carefully for the dpy integral part, this will again be the same thing, because here you have e to the power of minus py squared multiplied by beta by twice m minus beta omega squared by twice k. So now again the constant term is same, so you will be having here again the same integral result, root over pi by this beta by twice m minus beta omega squared by twice k. So all of this is done once. Then what you have is that you just have to multiply all of the terms that we have obtained from the solution separately and get the full solution. So this was the constant that we had left earlier, is that 2 pi by beta k to the power 3 by 2. Then the rest of the part is this this constant has appeared twice because this is coming from dpy and both dpx integral, so that takes out the root, and this is just simply root over, instead of root over, because it is been a squared of the root, so it is just pi by beta by twice m minus beta omega squared by twice k into this part that has been coming from the dpz integral. So this is root over 2m pi by beta. So we have solved it. We have solved the partition function for the single particle case for this harmonic trap, and this the whole function is looking like this, where you have 2m pi by beta to the power of half, then 2 pi by beta k to the power of 3 by 2, then your pi divided by beta by twice m minus beta omega squared by twice k. So this is the partition function. Our first step has been completed. Now using the partition function, you can just know what is the average of the entity of L squared, right? So this is the single particle partition function of harmonic trap. Okay. Now our question comes here that you have to calculate L squared average, where L squared is nothing but Lx squared plus Ly squared plus Lz squared. Okay, so if that is the case, then you just have to do is that you know what is the integral formula of this kind of a statistical average. Is basically you take the quantity, you multiply it by the Boltzmann factor to the power minus beta h minus beta omega z Lz here, because this is along z only. Then this whole thing you have to take an integral over all possible states of phase space, which is d cube p and d cube r, all going from minus infinity to plus infinity, all the integrals of p and xs. And below you have this whole thing, which is nothing but your partition function of single particle, that is z1. So you have already calculated for the denominator value, that is z1, and you just have to calculate the integral for the numerator separately, and then you can take a ratio and get the entire L square average value. Now this is going to be a long integral. You will see why, because there are so many terms that are present and you have to deal with it carefully. So first of all, you can break it down for our convenience, is that you can always break it down in separate summations, right? That is Lx square into the whole thing plus Ly square into the whole thing plus Lz square into the whole thing. Okay, so you can write it like Lx squared in the power minus beta h minus beta omega z Lz, then d cube p d cube r, this whole integral divided by z1 plus this Ly square into this whole thing divided by z1 plus this Lz square into the whole thing divided by z1. Okay, so if that can be done, then you can just write it down as separate things, that Lx squared plus Ly squared plus Lz squared. Now okay, so this is the thing that we want to do till now, and then if we can do that or not separately is because they are all individual terms, so you can in one way separate them out. So if that is Lx squared plus Ly squared plus Lz squared, each of the individual averages, then you just have to figure out what are the individual values of them, and you can just get to the final answer. So let us deal with each integral separately. So let's say this we take as 1, this as 2, and this as 3. So first of all we deal with the average of Lx squared, that is integral number 1, that is start to solve. So if you break it down now, put the value of Lx so that you can better understand it. So Lx is nothing but your x component of the angular momentum, which is just your ypz minus zpx. You can check it out from the cross product if you want, cross product of r and p, but this is the answer, this is the component. So if that is the case, then your Lx squared is nothing but your Lx is ypz minus z, sorry, this is not px, this will be py, ypz minus zpy, because there is a squared, so this will be a whole squared into your total, all the terms involving this energy terms, this p squared, which involves px squared plus py squared plus pz squared, then e to the power of minus half k r square, where r square means x squared plus y squared plus z squared, and then e to the power of minus beta omega into Lz, because omega is along z, so this is just xpy minus y px, and the whole integral I have taken one only single integral, also it will be divided by the whole partition function of z1. This is not a single integral, you know, because you have multiple, sorry, I have not put it down yet, so this you have multiple all the elements of dqp and dqr, so you have to also take that. Okay, so let us now try to solve one by one, get to solve one by one. So first of all, you have to break this down. So if this is a whole square format, that means you have y squared pz squared plus z squared py squared minus 2yz py and pz. So this is the thing, and the whole all other bunch of things, total integral divided by z1. So first of all, we'll only deal with the numerator part. That means we'll solve the integral first and then just divide it by z1, right? So okay, so if we can do that, that means let us first take the first term. What is the first term? First term is your y square pz square integral you have to make. So this is just 1 by z1, because all z1 comes in the denominator. So this is just 1 by z1 y squared, and because it is y square pz square, so let us first pz square at the side for now and only focus on what are the terms in y. So it is y squared, that is already present in y square pz square. Then again in the exponential you have e to the power beta into half ky square. This is another y dependent term. Then you have from the rotational part, you have this beta omega y px. Okay, and the whole thing goes under dy, because these are all y dependent terms. So you can just take a total integral of y together like this, and then all the rest of the terms are like x in or x in y, not y, x in z, p, x, py and pz. You have to take them separately. So what is happening here is that the x dependent terms are still left, e to the power beta k by 2x squared into also another x dependent terms is e to the power minus beta omega x py dx. Okay, and also the z dependent terms is just e to the power minus beta by 2k z squared into dz. Now again z terms is relatively simpler because z has no further dependence on any other term. So this is just a simple Gaussian integral again like before. So this will be easy to do. And you have also terms left as in px and py and pz, also the terms are left, that is e to the power minus beta px squared plus py squared plus pz squared divided by twice m and all the three elements of p. Now we'll deal with it later because you have this pz square also left, which you have to incorporate with this pz square to actually take the integral of dpz. But for now let us focus on these two integrals. First of all, this one, this is a simple Gaussian one. So this is nothing but your root over pi, where the constant is beta k by 2. So this is just 2 pi by beta k. So this part is done. Now if you try to focus on the the y squared part of the integral to solve only the terms dependent on y. So what you do is that you just take again a similar, you have to reduce it in a per typical Gaussian term, that is you have to take a e to the power minus beta k by 2 common, let's say. Okay, and um, so basically before that, before getting into y, we can also solve with taking the x first, right? After that I'll get to solve y. That way it will be easier. So let us first solve for x dependent terms. So this is just, again you have to similarly reduce it in a equivalent Gaussian term, which is just your integral of dx and then to the power of minus beta k by 2 into x squared plus 2 omega x py. So this is similar thing, similar integral that we had solved for solving z1 also. So you just directly put the answer that this is, you can reduce it in a Gaussian type of a form, and this will give you a 2 pi by beta. Okay, this I'll now, I am not solving it again because I just solved it earlier for the same type of solutions in solving z1. So you can just look it out from there. The structure is the same, so you can relate. So this is coming from your dx integral. Okay, from dx integral, and this part that we left already here is coming from your dz integral. Now you have also this dy integral left, where you have an additional term that is y squared that you have to take into account. So this is just e to the power, so this is y squared e to the power minus beta k by 2, then you take a common y squared, then minus 2 omega y px by k, and this whole thing is in dy from minus to plus infinity. Then again, if you try to reduce it in a similar whole square term, this integral, this exponential part, you will have that you have a constant term separated outside. So a similar thing, you just try to solve it in a plus b whole square or a minus b whole square format, so that a constant part comes outside the integral, which is e to the power beta omega squared px squared by 2k, and then you have this y square extra because this is already present in the term, and then e to the power of minus beta k by 2 y minus omega px by k whole square. So this is equivalent to a Gaussian form, only that if you replace this y minus this whole thing as t, then dy becomes dt, right? So yeah, so here we have to make a substitution of that variables, right? So you have to be careful if there is any problem in the solution or not, because there can be a mistake in the solution in this kind of a case. So just be very careful that you have this minus beta k by 2 y minus, there will be a minus sign because then omega px by k whole square. Now you introduce that you do a change of variables, that your t is equal to new variable equal to y minus omega px by k. So what is your y? Y is just your t plus omega px by k, right? And your dy equal to dt. So this integral here becomes reduced in the new variable terms, is that this is just your, this constant leaves outside, square by 2k, then this is minus to plus infinity, then y squared you have to put t plus omega px by k whole squared, then to the power of minus beta k by 2 t squared dt, right? So you just have a change in variable in from y to t. So by solving this, you know that you have to again break it down to t squared plus 2t omega px by k, a plus b whole squared, so it is omega squared px squared by k squared into to the power minus beta k by 2 t squared dt. Now if you look at each of the terms carefully, it is just a constant term into, now break each of the terms separately. So this is t squared into e to the power minus beta k by 2 t squared dt, then plus 2 omega px by k, then minus to plus infinity t e to the power of minus beta k by 2 t square dt plus omega squared px squared by k squared minus to plus infinity to the power minus beta k by 2 t squared dt. So you have three terms. If you look carefully, then each of the answers you know very well from the standard Gaussian solutions. I just wrote it down previously for you, that when you have this kind of a t square term, then you have 1 by 2a root over pi by a form, where a is your constant. And when you have such in odd value, that is t times t to the power odd power, which is t to the power 1 times this Gaussian form of this whole square exponential, then you have this integral value as 0. And this last term is the simple Gaussian integral, giving you a root over pi by the constant, right? So if you have to write down the results, then you can directly do them because you know the standard integral values. This is this whole constant into this thing is nothing but 1 by 2 into the constant is beta k by 2, right? So this is this, and then root over pi divided by beta k by 2 plus this is 0 plus the third term is omega squared px squared by k squared into root over pi by beta k by 2. So what you have in hand is now you can take the common factor out. So this is per beta omega squared px squared by 2k squared into root over of 2 pi by beta k into this is 1 by beta k plus omega squared px squared by k squared. So this is your final answer, and this is coming from the dy integral, obviously. Okay, so hopefully this part is correct. I have not missed out any term. Okay, let us see now what happens forward. So we have solved up to this point dy integral, then this from dx integral and the dz integral. Now we are left with all the px, py and pz part. Okay, so for the pz, first of all you have to take this pz square also into account, then this e to the power of beta pz square by twice m into account, and where else you have pz, you do not have pz anywhere else, so that is done. And for px, you have also px present in the other parts like here and here. And for py, if you have py anywhere else, is that here you have a py, so that you have also to consider with the other parts. So let us do that. First of all, let us try to solve for the pz part. So pz integral is nothing but minus to plus infinity pz square e to the power minus beta pz squared by twice m dpz. So this is just a simple Gaussian, you know the formula, that this is just root over pi by beta by twice m, that is root over 2m pi by beta. So this is coming from your dpz integral. Similarly, if you solve for the dpx and dpy parts, so what you have is that, first let me tell you what is the dpy part. Let us try with the easier one first. So we have one dpy here, e to the power beta omega squared py squared by 2k. So this is e to the power beta omega squared py squared by 2k, and also you have another e to the power minus beta py squared by twice m and nothing else dpy. So we can again reduce it to a equivalent Gaussian. So e to the power minus py squared to beta by twice m minus beta omega squared by twice k dpy minus 2 plus infinity. So this is nothing but your root over pi by beta by twice m minus beta omega squared by twice k. So this part is done. This is coming from your dpy integral. Okay. and this dpz is done. So only left with dpx integral, which will involve this value, this exponential beta, this as px. So let us take the whole term. So this is, let's take it. So if you, for the px integral, you know that this is dpx to power beta omega squared px squared by twice k into root over 2 pi by beta k into 1 by beta k plus this thing. So plus omega squared px squared by k squared. So and alongside you have also minus beta px squared by twice m. This is your whole px dependence in the integral. So all the constant parts first of all outside, that is root over 2 pi by beta k. Then for the first term you have a term multiplied this constant term with these two terms in dpx. So for the first term you have just 1 by beta k into, this is just the same thing, right? Px squared common minus px squared common, and you have beta by twice m minus beta omega squared by twice k as a constant term. So the Gaussian will give you root over pi by beta by twice m minus beta omega squared by twice k. And for the second part you have this constant as omega squared by k squared outside, and then you have also a px squared term present, right? So what is this term if you want to write it down separately? So this is basically, let us write it down in separate ink. So this is your px squared e to the power minus px squared into beta by twice m minus beta omega squared by twice k minus beta omega squared by twice k. This is from minus to plus infinity dpx. So this is again a reduced Gaussian form where this is the constant, and because there is also px squared term in present to the front, so this is just 1 by 2 times the constant, which is beta by twice m minus beta omega squared by twice k into root over of pi by again this constant beta by twice m minus beta omega squared by twice k. So we'll just replace this value here in the second part of the solution. So this is just 1 by 2 beta by twice m minus beta omega squared by twice k root over 2 pi by beta by twice m minus beta omega squared by twice m. Okay, so this is done. So the whole thing is now, if you just take a multiplication, so this will become this factor is common, right? So you can take it out as common, root over 2 pi by beta k root over of pi by beta by twice m minus beta omega squared by twice k into 1 by beta k plus, what is this, omega squared by k squared to beta by twice m minus beta omega squared by twice k. So this is the whole thing coming from your final part, which is your dpx integral. So all the parts are done now. Okay, now it is the time to combine all of this together so that we can now take the whole thing of the whole y square pz square integral result is equal to, now remember that from the starting again we actually ignored this 1 by z1 thing actually. Okay, so you have to take it into account, and I think also a 1 by h cube was missing, right? Because yeah, 1 by h cube we have to take. Just let me check 1 second. Because if you just go back in the question, So in the question you have no h cube part left, because your h cube, I missed out one term, because there should be also an h cube in the numerator integration, just like I put a h cube in the z1 integral. Similarly, when you are taking the statistical average and then taking the integral, like here the average of L square, then not only this will suffice, but there will be a phase, because there is a phase space integral, right? So you have to take a 1 by h cube also here. So all of the cases, this will not be just z1 but also a z1 times h cube that is coming from the integral in the numerator, right? So all the things will have a 1 by h cube, which you missed out, and we will adjust later. Okay, so we'll have a 1 by h cube in all the terms. So that's what I am adjusting right now. So this is 1 by z1 value we know, we'll put it separately, 1 by z1 h cube, and then just take the multiplication of all the separate terms, like what are the terms that are coming from the starting. So this is your from dz, so root over 2 pi by beta k into dx root over 2 pi by beta k 2, so this is 2 times root over 2 pi by beta k, and then okay, so this part is not taken because lastly this part was involved inside the py integral, so we will not take that. And then the dy integral, you have you have to again consider the dy integral, because some parts of it are constant and some part has still px part, right? So it is involved in the px integral. So again you have to wait for the dpx integral result for writing the final result. Then the constant part from dpz integral is root over 2m pi by beta, and this is dpy root over. So let us start to write it down. So first of all, you have root over 2 pi by beta k 2 times, so this is whole square, into from dpz integral you have root over 2m pi by beta. Then from dpy you have root over pi by this whole thing, so this is root over pi by beta by twice m minus beta omega squared by twice k, into finally this dpx integral part is root over 2 pi by beta k into another this factor root over pi by beta by twice m minus beta omega squared by twice k, into you are multiplied by 1 by beta k plus omega squared divided by 2k squared beta by twice m minus beta omega squared by twice k. Okay, so if that is the case, then let us simplify. This is 1 by z1 h cube, this is 2 pi by beta k to the power 3 by 2, because you have 3 such terms here and here. Then you have single root over 2m pi by beta. Then you have this term twice, so you just take out the square root, and this is a simple beta by twice m minus beta omega squared by twice k. Then you have 1 by, this is the rest of the term is 1 by beta k plus omega squared 2k squared beta by twice m minus beta omega squared by twice k. Okay, so what you have is that now this thing is what you have in total, but you also know the value of z1, so you can just divide and get what is a simplified value. So let us look at what was z value. Z1 value is this 1 by h cube, this thing and this. So we have to divide it by z1. So here your z1 value, let me write it down again for you. So this was your 1 by h cube into 2 pi by beta k to the power 3 by 2 to root over 2m pi by beta, and then also pi by beta by twice m minus beta omega squared by twice k. So if you divide z1, you see that you cancel out all these terms, like this term, this term, this term and this term, all those are cancelled out. Only you are left with, so y square pz square integral gives you equal to 1 by beta k plus omega squared by 2k squared into beta by twice m minus beta omega squared by twice k. So this is the whole factor that you obtain from the first integral. So obviously this was a pretty huge integral. You have to take step by step to get the whole thing right. Now if you remember that not only y square pz square part, but also you have to solve the other parts of the whole square part, which is like the second term is involving an integral of um, z square py square part. Again this part you have to take the whole integral, like involving all the other terms. So just like you did for y square pz square, here also you take a division of 1 by z1 z h cube and then z square py square and the whole into part this whole thing, then all the d cube p d cube r. Okay, so this thing you again have to repeat just like you did for the last case. So just the same approach, only you have to consider what are the different terms, because depending on how you deal with the terms the answer changes a little bit, but the approach is the same. So we'll solve it accordingly. So you have your py squared. Okay, so I may not solve the whole part of it, because again after I have solved that part number 2, then part number 3 sorry part number 2 I mean, let me point it out. So after I have solved this part for Lx squared average, okay, Lx squared average involves this whole summation of y square pz square integral z square py square and this integral. So once I have solved for that, then by the similar approach you can just solve for yourself what is integral number 2 and 3, and then you can add those three up, and you will get that, you will exactly get the answer what is given in the options. Okay, so I will not probably solve all of them because it will be again the repetition of the same things. I'll just tell you the way to do it for 2 or 3 cases, and then the rest of it you can solve for yourself. So if I am doing the second part of the integral, which is z square py square integral, so I can just separate py square first and then only take the dependencies in z, which is like z square e to the power of minus beta k z squared by 2 dz, and then for dx you have e to the power minus beta kx squared by 2 e to the power of minus beta x py dx. Okay, and for dy you have e to the power of minus beta ky squared by 2 e to the power plus beta y px, and this was your dy. So your dz, dy and dx are done, and then you are only left with all the dpx forms, which is nothing but your beta by twice m px squared plus py squared plus pz squared. We leave that out for later, because once you have solved for x, y and z integral, you will have terms involving these, so then we'll solve these integrals. Okay, so first of all focus on these parts. So first this is, z1 is easy because this is simply a standard Gaussian form, where you have to take 2 1 by 2 beta k by 2 root over pi by beta k by 2. So this is 1 by beta k root over of 2 pi by beta k. Okay, and this thing is again familiar to you. This thing we have solved earlier also how to solve it. So this will just give you a constant of e to the power of beta omega squared py squared by 2k. I think this was the thing. Let me check, because this will have a similar answer. Mm, yeah, so this will be 1 second. will be like, in this case, I think, yeah, this kind of integrals will be the same to this. So what we are left with is just e to the power a constant factor of beta some omega squared, that p squared by twice k into root over the 2 pi by beta k. So the similar thing will be done here. Same approach is that for this dx integral you have e to the power beta omega squared py squared by 2k into root over of 2 pi by beta k. Alright, and for the dpy case, again the same thing. So let me box it out. So this is from dz solution. Okay, this one here from dx integral part, and for the dy part you have the same thing, similar approach, only e to the power beta omega square px squared by twice k into root over of 2 pi by beta k. So this is your solution from the integral of dy from dx, from dy, from dz. And what is then dpx, dpy, dpz? You have to take the remaining terms. First of all, you have already a py square here, right? So let us take first what is a pz square component. So pz do not have much of the terms, so you just have e to the power minus beta pz squared by twice n and dpz. Okay, so this will just give you root over of 2m pi by beta. So let us box it out. So this is from dpz. Similarly, if you take what is the contribution from px, so then you know that you have px in two terms, that is e to the power minus beta px squared by twice m, and here is this other term e to the power of to the power plus beta omega squared px squared by twice k and dpx, and this is again from minus to plus infinity. So you can reduce it in a Gaussian form by taking the constant out, and this will just be root over of pi by beta by twice. And again, this is familiar to you. I do not need to elaborate. Same approach. So this is the thing. Let us box it out. This is from dpx. And we are only left with dpy. Now dpi has a slightly different approach, but this is again something you have done before. So you have now py squared also. Then e to the power of minus py squared into beta by twice m minus beta omega squared by twice k dpy. So again you can see that you have to follow the same manner I had followed earlier for solving out these y integral before. So let me go back. Yeah, so you see that this was your y integral, right? Before you had solved it, but now instead of y you just have py and nothing else changes. Everything else is the same. Okay, sorry, on one other thing is different. Sorry, it is not exactly similar. So let us again solve it, right? Not leave any confusion, because this has this whole thing as constant and py. So no, this is not exactly the same. I was wrong, because this has this constant outside, and you can just have a standard Gaussian form as 1 by 2 times the constant, which is beta by twice m minus beta omega squared by twice k. Okay, this thing, and root over pi by that same constant. So this is taken from dpy integral. Then your whole integral becomes whole py squared z square integral becomes 1 by z1 h cube into, you have to collect the separate terms. So what are the separate terms? First of all, you have this 1 by beta k root over 2 pi by beta k. So you have 3 2 pi by beta k's. So 2 pi by beta k to the power 3 by 2 into 1 by beta k into 1 root over 2m pi by beta into, you have two these terms, so the square root actually vanishes and it is a simple term. So let us write it down. So it is our 2 pi by beta k to the power 3 by 2 into 1 by beta k into root over of 2m pi by beta into this part. So this is 1 by 2 times beta by twice m minus beta omega squared by twice k into pi by beta by twice m minus beta omega squared by twice k. Now if you remember what was the expression of z1, you will see that when you have a 1 by z1 term, all these factors will be cancelling out. This term, this term, this term, this term, and what else was there? Yeah, these will be the terms. This thing will be left and this thing will be left. So you will have 1 by beta k into 1 by 2 beta by twice m minus beta omega squared by twice k. Okay. So this is just 1 by, just write it down together. So this is just 1 by 2 beta k. So this is your whole thing. So this is coming from the pz squared and sorry, this is py squared z squared part, py squared z squared integral, and the rest of the terms in the whole square was just the part of this thing, right? 2yz py pz, right? But this part is relatively easier because you see that when you have this 2yz py bz and this whole e to the power minus something and whole d cube p and d cube r, you see one thing just strikes you immediately, that you have z dependence only in two terms, this only in three terms. One is z itself, and then you have e to the power of minus beta k by 2 z square, and you have dz, right? No other terms have any z dependence. But you have y dependence in another term because you have dot sigma dot L term has a y px part, right? So if you only focus on the z dependence, then you see this is the whole z part, nothing else depends on z here, and this is clearly an odd integral over Gaussian, so this will give you a 0. So once one of the term is 0, the whole product term becomes 0. So basically your entire this Lx squared integral, if I have to write it down, Lx square integral, where basically your this thing, right, y squared pz squared plus z squared py squared plus 2yz py pz, and you have now seen that this part goes to 0, and these two parts I have already calculated. So I'll just write down what are their summations. So one part is this thing here, and the rest of the part was earlier. So your y square pz square integral was here, this thing, 1 by beta k plus this omega squared by 2k squared divided by beta by twice m minus beta omega squared by twice k, 1 by beta squared. So this is your, sorry, I just forgot, 1 by beta k plus omega squared by 2k squared, omega squared by 2k squared into this whole thing beta by twice m minus beta omega squared by twice k plus this z square py square average is here. So 1 by 2 beta k into this term you can just go ahead and simplify it further by taking 2 beta k squared, in fact, beta by twice m minus beta omega squared by twice k. So the first part has 2k into this term missing, so you have 2k to beta by twice m. And the second part has just a beta missing, and the third part has beta k square, just a k missing, so this thing. And if you simplify, it is your beta k by m, so beta k by m minus beta omega squared, 2k by 2k cancels out, plus beta omega squared plus k, this and this cancels out, and you have 2 beta k squared beta by twice m minus beta omega squared by twice k. So if you want, you can simplify it even further, just as much as you like it. So this is or you can leave it like that, and later on you can adjust the answer or simplification as you have. So just leave it as beta by k, take out as common, so this is beta by m plus 1 divided by 2 beta k squared into this whole constant, so this k and k cancels out, so you just have 1 by 2 beta k beta by m plus 1 divided by beta by twice m minus beta omega square by twice k. This is the whole thing. So now you have got the answer for LX squared average. You can do the similar thing for, I will not do it again because this is just the same thing, but instead of here the formula will be, because it is Ly, so it is z squared px squared plus x squared pz squared. So this is basically average of zpx plus x, sorry, zpx plus xpz whole square. That means z square px square plus x square pz square plus 2xz px pz, and the whole thing in average. Okay, so if that is the case, then you just have to do the same thing again, do the entire integral term by term, and this last part again will give you 0, so this you do not have to bother about. And again for Lz square, what will it be? So it is just xpy plus y px whole square. Now here you have to be a little conscious because there are several terms and none of the terms I think will become 0. Okay, because it is now involved in all px and py part, and in all of the integrals you have py and px present, y and x present. So here you have to go term by term and solve the whole thing, but the approach and the type of integrals you will face will just be the same as we have done for the earlier integrals. And finally, when you get each one of them separately, so you have to take the whole thing. Okay, and when you get each one of them separately, then you can just take the whole L square as a summation of all of them. Okay, and just sum it up and you will get your final answer. Okay, so hopefully if you just go on doing it by yourself, you will get to the answer, but I have just shown you for multiple cases how will be the integral types and how should they be solved. Okay, so you can already start to see that you have this omega squared type of factor over here. So if you work that out further, I think you will have a similar thing, but actually you have to see that whether the answer actually matches or not, because other than that, the type of the answer that I have given you will be that you have to just follow the same thing. Okay, so we have just 2 questions left. Let me check how much time. Okay, so we do not have much time, so let us quickly finish it up. We have already crossed 2 hours. So for this third question, this is easy because you have a formula given. Okay, if I summation is given as this integral where the remainder term is r has a specific form given as this, and the form of the function is also given as fx to the power minus alpha mod x where the alpha value is greater than 0. Okay, and it is said that if your r value, that is the remainder value, is 1% of the approximate answer, that is this. So your r value is 1% of this thing, then what is the value of, I think what is the value of, what is asked here is alpha value, I think. Yeah, alpha value you have to get. So let us solve it quickly. It is not very difficult, short problem. Okay, so question number 3 tells you that your function fx is e to the power of minus alpha mod x where alpha is greater than 0, and in the integral you have the condition is that r is 1% of the approximate answer, which is nothing but 0 to infinity fx dx plus half f of 0. So you see that the integral is only from 0 to infinity, that means only for positive side of x. So that means 0 to the power minus mod x of alpha is nothing but just 0 to the power alpha x, because alpha x is also greater than 0 under this limit. So you can just write down mod x as just simple x. Okay, so this integral is what? This is 0 to infinity e to the power of minus alpha x dx plus half into f of 0 means e to the power of minus alpha into 0, which is nothing but e to the power 0, that is 1. And as this integral is e to the power minus alpha x by minus alpha going from 0 to infinity, and this is half into 1, which makes it half, and this is just minus 1 by alpha e to the power minus infinity minus e to the power 0 plus half. This is minus 1 by alpha e to the power minus infinity is 0 minus 1 plus half. So this is half plus 1 by alpha, right? And this so one part is done. Now the remainder r is given as minus 1 by 12 f prime 0. So your f prime is derivative of fx, so this is nothing but minus alpha e to the power of minus alpha x at x equal to 0, which is nothing but plus alpha by 12 into e to the power 0, which is 1. So this is just alpha by 12. Okay, so if that is the case, then your remainder alpha by 12 is taken as 1% of this whole thing, 1 by 2 plus 1 by alpha. So 1 by 2 plus 1 by alpha into 1 by 100. This is your condition. Now just you have to solve the equation for alpha, nothing else. So this is alpha by 12 equal to 1 by 200 plus 1 by 100 times alpha. So you can just solve it, take it to one side, 100 alpha square, so just take the alpha to one side, alpha by 12 minus 1 by 100 alpha equal to 1 by 200. So this is 100 alpha squared minus 12 so this is 1200 alpha. This is 100 alpha squared minus 12 equal to 1 by 200. So this 200 and 1200 cancels out, so this is just 6. So this is nothing but your 100 alpha squared minus 12 equal to 6 alpha. So you have to deal with this kind of a quadratic equation, and you know how to solve it. So the idea is that you take alpha equal to minus 100 plus minus root over of, sorry, this is not minus 100, this will be minus of minus 6. So this is plus 6, because you know that whenever you have ax squared plus bx plus c equal to 0 solve type of equation, you solve x by minus b plus minus b squared minus 4ac by 2a. So this is minus of minus 6 plus minus b squared minus 4 into a into c by 2 into a, right? So this is just alpha equal to 6 plus minus root over 36 minus minus plus 5800 divided by 200. So you can now calculate that this is just 6 plus minus root over of 4836 by 200. Now it is mentioned that alpha is positive and real also. So you cannot take the minus part. You just have to take the plus of the root. So this is just 4836 by 200. If you calculate the square root, you will get that this is almost 6 plus 69.5413 divided by 200. Just use your calculator, and this is almost equal to 0.37707. If you look at the question, you will see that this is your solution. This is matching. So we have solved question number 3 also, and now we are only left with question number 4. So question number 3 matches with our solution, right? And question number 4 is nothing very difficult. Again, the same Legendre transform type of a problem. I have already solved a similar type of problem to you before in some of the assignment number 3, I think. So the approach will be the same. You know the basic idea of Legendre transform, then it will be very easy. The idea I will repeat is that when you are wanting to transform a function of dependence on x variable to another new function which has a dependence on a new variable y, where y and x are related by y equal to df dx. So how do you make that change or transformation? Is that you take f star y, the new function, as your old function fx minus x times the new variable y. Okay. So the similar thing we'll do here. Here in our case, your S is a function of all the internal energy, volume and number of particles, U, V and N. Now this is your initial function. You have to transform it to A star, where it becomes function of the other variables which are the opposite variables of these things. Like if you want to change from U, V and N, so you have to change it to its conjugate variables. Like for T, you have to take, just here it is mentioned that for internal energy you have to trade it by temperature. So you have to transform the variable dependence to temperature. For volume you have to transform it to pressure. And for number of particles you have to change it to chemical potential. So this is the case. So basically you have to change it to T, then P and mu. So how to do that transformation? So basically I'll do it here on the side. First of all, you have to take the primary form, that you take the initial function and u minus xy. Here means that you take, first of all, for u it is minus u times del s del u. Then to trade off for v you have to take minus v del s del v. Then for trade off for n you have to take minus n del s del n. Now you have to get the answer of these derivatives over s, like that you can get from the first law of thermodynamics, that Tds equal to du plus Pdv minus mu dn. You know that from first law of thermodynamics. Okay. So from here you get that your del s del u is just your 1 by t when all the other terms, that v and n, are constant. Same del s del v is just your p by t when the other terms u and n are constant. And your del s by del n when v and u are constant is nothing but minus mu by t. So from here you can get the derivative values and you can just directly put it here. So this is just s minus u del s del u is 1 by t minus v del s del v is p by t and del s del n is minus mu by t. Okay. So basically if that is the case, you get s minus u by t minus pv by t plus mu n by t. So this is your transformed Legendre transformed entropy, s minus u by t minus pv by t plus mu n by t. Let us see why, if the answer matches. So you can see that clearly this is our answer, s minus u by t plus mu n by t minus pv by t. So with this we are done with the solution of assignment number 7, and we have done all the solutions, and also the class time is also finished over more than 2 hours. So I'll just stop the class here. Okay, so this is the last tutorial we are having.